Consider again our example of two conductors separated by an insulator. We said that the capacitance of this capacitor we see here, or any capacitor for that matter, depends only on the geometry of the configuration and nothing else. In that case, for us to find a general formula for the capacitance here in terms of the geometries, it turns out that this is quite a difficult example for that. Like we said before, the charge distributions are non-uniform, and it's just going to be an absolute mess. So why don't we choose something much easier and work our way up from there? Let's try to find the capacitance of two parallel conducting plates. One of the plates has some charge positive Q, and the other plate has some equal and opposite charge negative Q. Then the potential difference between the two plates we can find by considering the electric field between the two plates. Now, as long as the plates are close together and they're sufficiently large, then the electric field between the two plates is roughly perpendicular to the plates. This approximation works really well as long as L, the length of each plate, and W, the width of each plate, are much larger than D, the distance between the two plates. Of course, in the illustration we have here, D looks actually quite comparable to W and L, but it's just an illustration. We want to actually be able to see the electric field lines here. But in reality, D is much smaller than L and W in practice. If the electric field due to one of the single plates is perpendicular to the plate, then we've actually seen how to solve for the electric field previously. In one of our calculus-based exercises, we found out that the magnitude of the electric field due to a large plate with some surface charge density sigma is given by sigma over 2 epsilon naught, and it's uniform on each side of the plate. In that case, the electric field due to the positive plate is sigma over 2 epsilon naught pointing away from that plate, and the electric field due to the negative plate is sigma over 2 epsilon naught pointing towards the plate. So when we take the superposition of these electric fields from the two plates, we have the magnitude is 2 sigma over 2 epsilon naught, or just sigma over epsilon naught, as the electric field between two plates, where sigma is the magnitude of the surface charge density on one of the plates. It's okay to just add their magnitudes here since the vectors are parallel. Now, how do we break down sigma further? Sigma is just the charge per unit area of one of the plates, or just Q over A, where Q is the charge on one of the plates and A is the area of that plate. So that means we can write the magnitude of the electric field as Q over epsilon naught times A. If we wanted the electric potential difference between the two plates, then in essence we just have to multiply this electric field magnitude by the distance between the two plates, which we said was lowercase d. And that gives us the potential difference between the two plates, up to a sign. Now let's try to remember what we were after. We want the capacitance, which is Q over delta V. We're so close, so how do we get to that final result? What do we do now? Up there we have charge and potential difference in the same equation. So if we rearrange it a bit, we can end up solving for Q over delta V, which is the capacitance of this two-plate configuration. That's how capacitance is defined. The capacitance then is epsilon naught times A over D. A here is the area of one of the plates, and D is the distance between the two plates. Note that the only two parameters, A and D, are geometric parameters of the capacitor itself. So this is the true capacitance of the object, even if there were no charge and no potential difference on the capacitor. This is an expression worth memorizing, but in case you need to refresh your memory, now you know which video to pop back to. That wasn't too difficult of an example, but we can find working with some capacitors to be just a bit more difficult, and they usually require calculus. For instance, one way to design a capacitor would be to have one cylindrical shell enclosing another cylindrical shell inside. Each shell is a conductor, and the pair of shells makes up a capacitor. If you wanted to find a formula for the general capacitance of this configuration, you would start by taking one of the plates to be positive Q, and the other as negative Q. Then you want to find the potential difference between these two conductors by taking advantage of the radial symmetry in the electric field, and then you would go to town from there. Another way you could create a capacitor would be having a spherical conductor enclosing some other spherical conductor. The general process for finding the capacitance of something like this would be to imagine if you had a positive charge on one of the conductors, say the inside one, and an exactly equal and opposite negative charge on the other conductor. Now that we've imagined that, what is the potential difference between these two conductors? Again, we want to take advantage of the radial symmetry in the electric field, and actually, why don't we change the colors here so they're not so bright? Much better. Again, if we want the formula for the capacitance, we need the potential difference. So we find that by integrating the electric field inside between the inner radius and the outer radius. Once you've done that, then you just take the magnitude of the charge on one of the conductors and divide it by the magnitude of the potential difference. And that would give you the capacitance for this set of conductors, or this capacitor. Remember, capacitance is always a positive value, so we're talking about all magnitudes here. The magnitude of charge divided by the magnitude of the potential difference. All that being said, what a weird looking capacitor, don't you agree?
And it's spherical! Spherical!
We see that in both of these examples, we need calculus to find the potential difference between the two conductors, because the electric field is changing between them. That's the only place we need calculus, though. The rest is quite straightforward algebra. We'll go over some of these different types of capacitors in the exercises and problems.